So now we know about the resting membrane potential, we know about the action potential, we know about leakage channels, we know about sodium-potassium pumps, we know about voltage-gated sodium channels. You know a lot, right? Now, we were getting here to the point where we were talking about the action potentials. One of the things that I told you was that one voltage-gated channel will cause sodium to leak into the cell, and that when that happens, that will change this part of the membrane's voltage, and that'll open up the next channel. But here's the thing. The thing is that when we have an action potential, we want that action potential, that's supposed to be a nerve cell, we want that action potential to travel this way. And we want it to end here. And then we want the cell to be able to reset its resting membrane potential. Do you see the problem with voltage-gated channels? The problem with voltage-gated channels is that when this voltage-gated channel lets sodium go in, some of the sodium goes that way. So the question is, why is it that the action potential only goes in one direction? Because if it really is as simple as what I've told you, then not only would this voltage-gated sodium channel cause this gate to open, but this voltage-gated channel would keep that gate open. And if that happened, then you'd have to use a neuron one time and throw it away. And clearly we don't do that. Why is it that we don't have to do that? And that has everything to do with the fact that every one of these voltage-gated sodium channels does not just have an open setting and a closed setting. It's got an open setting, it's got a refractory setting, and it has a closed setting, okay? So let's start with the closed setting. Here we've got the closed setting, and in the closed setting, you can see that no sodium could go through there because it's closed, right? Now, a change in voltage would cause it to open. Now that it's open, sodium can go through, sodium goes through, great. After a short moment, this voltage-gated sodium channel goes into what's known as its refractory period, where it is not allowing sodium to go through, and it cannot be opened by voltage. So they show that this part of the protein is kind of like a little ball, and it just like gums up the works. This is the situation that allows the potassium, voltage-gated potassium channels to do their thing, and then the action potential runs down the length of the axon, and it's not until the next voltage-gated sodium channel has gone into its refractory period that this one is going to go into its regular open, ready for being activated period. So voltage-gated sodium channels have more than two settings. They're not, most of the channels are either open or they're closed. Voltage-gated sodium channel is different. It can be closed, in which case a change in voltage will open it. It can be open, in which case sodium's flowing through it, or it can be in this refractory period where it doesn't care what the damn voltage is, and it also won't let sodium go through it. And then it goes back to being closed, but vulnerable to being opened by voltage. Pretty cool, huh? All right, let's answer a question. Which of the following statements is false? You may want to just pause the video, look for the answer yourself. Otherwise, I'm going to walk through the question with you. Inside of each neuron is negatively charged. Okay, maybe you don't like the way I phrased that, but I wasn't trying to be tricky. It's true. So we're going to say that one is true. Potassium leakage channels help the nerve cell establish its resting potential. What are the two proteins that set up the resting membrane potential? The sodium-potassium pump and the potassium leakage channels. These are the two proteins. Remember that chart? Okay. These both set up the resting membrane potential, so this is true. We're looking for which one is false, okay? Sodium-potassium pumps require ATP. That's why their other name is sodium-potassium ATPase. So I hope number 3 is the one that is false. Voltage-gated sodium channels help the nerve cell establishing its resting membrane potential. Is one of those a voltage-gated sodium channel? No. Those are the two that do resting membrane potential. This one does action potential. So the one that is false is number 3. Okay. Voila. Good deal. Oh, another question. Voltage-gated sodium channels. Okay, voltage-gated sodium channels. Okay. There are proteins that use ATP. No. Pumps use ATP or pumps get called sodium-potassium ATPase. Open when the proper molecule binds to the protein. No. If this was true, this would be a ligand-gated channel. So that's not true. Pumps potassium out of the cell. Wrong. Channels are not pumps. So that's talking about the sodium, but actually that's not even talking about the sodium potassium pump. Allow sodium to enter the cell. Okay, that's true. When they're open, they do. I'm not trying to be tricky. When they're open, they do. Allow the nerve cell to make an action potential, absolutely. So the right answer is both 4 and 5 are true. Right? What if that was one of those select all that apply? Would you get them both right? Right. Now, before we conclude this little video, let's talk about how local anesthetics work. The most common local anesthetic is lidocaine. Lidocaine and its derivatives like bupivacaine or whatever, they work by blocking the voltage-gated channels. So here I've got my lidocaine as this pretty purple-blue triangle, and you can see it's blocked the voltage-gated channel, voltage-gated sodium channel. So the sodium-potassium pump did its thing. Potassium leakage channel did its thing. And then it's true that the membrane got changed. Oh, sorry. That's not supposed to happen. What's supposed to happen is the sodium tries to get in and it can't get in because the lidocaine is sitting right there in the voltage-gated sodium channel, blocking the way so sodium can't go through. So when you've got an injection of lidocaine, like from the dentist, the cell body knows that there's pain and is trying to send the message to your brain, ow, but the message starts going down there, but it gets stopped because these voltage-gated channels have blocked the passage of the information. All right, let's see. Yeah, we're going to start here at what is it that initiates an action potential. We're going to start here at the beginning of the next video.